Good day to everyone and welcome. Thank you for finding time and attending today's webinar, Understanding Surface Area Measurement and Techniques. My name is Jeff Kenvin, and I'm the Technical Director at Micromeritics Instrument Corporation, a global leader in material characterization technology. I'll be your moderator for today. Our speaker for today is Jack Saad, an associate scientist and our global technical training and support manager. Jack received his chemistry degree from the University of Georgia. He joined Micromeritics shortly after obtaining his degree, and then spent the early part of his career in the pharmaceutical industry. He rejoined Micromeritics in 2011 for particle size applications. He's also been instrumental in our global technical training program, where we've created www.micro.edu for training and e-learning for our users. Before we start, let me explain a few of the things we'll do during today's webinar. If you have any questions on the content presented, raise them over the phone or write them to chat in our Q&A session at the end of the webinar. The webinar recording will be available on our webinar landing page, so make sure you check back in around 1.5 weeks. But you'll also be provided a link to the recorded webinar via email once available. Now let's get started. I'm pleased to introduce today's speaker, Jack Saad, who is going to be speaking on understanding surface area measurement techniques. I'm handing it over to Jack now to learn more about surface area and measurement.
Thank you for the introduction, and thank you all for attending today's webinar. Again, my name is Jack Saad. I'm part of the scientific staff at Micromeritics Instrument Corporation, and my talk today is about surface area measurement techniques. And the idea is understanding how these techniques measure surface area, and how can we use this to better our understanding of the data that we collect and improve our interpretations. I'll start with an overview of the topics that I'll be discussing today. I'll start with an introduction to surface area, and then discuss the relationship between surface area and particle size. In order to do this, we'll need to use density values. So we use gas picnometry to calculate the density. The reason why this is important is that two of the techniques we'll be using to determine surface area are primarily particle sizing techniques. So this relationship between particle size and surface area is important, and density is an important part of that calculation. And the techniques we'll be looking at for surface area are BET method by gas adsorption, air permeability, and laser diffraction. And then go on to look at some case study data where we collected some surface area measurement data on 3 powdered metals, and comparing those along with comparing the techniques, and then provide some concluding statements. Specific surface area is defined as the exposed extent of a sample surface, both external and internal, per unit of material. Activity and reactivity of a material directly relates to the exposed surface of the material. The amount of binders, surfactants, coatings, and so forth to cover a sample surface is a function of the total exposed surface. When I'm referring to external surface, this is only dependent on particle size and particle shape. Internal surface is dependent on the porosity of the particles. Now I want to turn our attention to the relationship between surface area and particle size. Typically when we talk about particle size, we're referring to equivalent spherical diameter. So if we're talking about a sphere, we can calculate the volume of a sphere from the radius. We can also talk about the surface area of a sphere in terms of radius. So we now have particle area, surface area, and a volume. If we put these equations together, we can look at the relationship between area per unit of volume in terms of 6 divided by the diameter. We further can use the density of the material and calculate a mass if we know the volume. So from the volume and the density, we can calculate the mass. We put these equations together to calculate specific surface area per unit of mass, and we get the relationship as 6 divided by the diameter times the density. Now keep in mind we're talking about non-porous materials. In this case, simple geometry is like a sphere. So again, for a sphere, we have this relationship as area divided by the volume is equal to 6 divided by the diameter of a sphere. Well, if we think about another geometric shape, a simple geometric shape as a cube, the area is 6 times the length squared. Volume is the length of the side to the third power. So if we apply the same type of calculation of area divided by the volume, we can simplify it in terms of 6 divided by the length of the cube. So you can see it's the same type of relationship as a sphere. So it works really well relating volume and area. Then we actually look at a cube, we can see the volume occupied by 1 centimeter cube. The surface area is 6 centimeters squared. However, if we divide that cube up into smaller and smaller pieces, but they still occupy the same volume, the surface area increases as the particles get smaller and smaller and smaller. So imagine also if these particles are not actually particles, but they're pores. If you actually think of it as a solid 1 cube, but you increase the size or increase the pores, the number of pores, as you increase the number of pores, you're also increasing the surface area in the similar manner. As noted in the previous slide, we need the density of the material in order to relate surface area to particle size. Density is defined as the mass of material per unit of volume. We use gas picnometry, which is a gas displacement method, and we look for the volume of gas displaced by the material in order to calculate the skeletal volume or skeletal density. This technique uses the ideal gas law to make this determination. This technique dates back to Archimedes in 2050 BC, so it's been around for quite a while, actually. And we look for the true volume of a material with an irregular shape by displacing, in the case of gas picnometry, displacing a gas. In the case of Archimedes, displacing water. Before I start getting into surface area calculations by the different methods, and specifically the BET method, I want to give a little background on physical adsorption. Physical adsorption is a concentration of gas molecules at or near a solid surface. Molecules from the gas phase strike the surface at equilibrium. Their rate of condensation is equal to the rate of desorption. Desorption is, of course, when the molecules of the gas are coming off the surface. We're looking for a constant surface coverage at equilibrium. Surface features change the adsorption potential. Curved surfaces or roughness provide enhanced adsorption potential. In this illustration, molecule D has the higher surface adsorption potential, while molecules A, B, and C have lower potentials. Molecule E is the typical surface adsorption potential on a flat surface that's homogeneous. This leads us to the first surface area technique, which is the BET method. BET stands for Brunner, Emmett, and Teller. This method was established in 1938, and it's an estimate of the monolayer capacity. The monolayer being the first layer of molecules adsorbed to the surface. It does take into account multi-layer adsorption, and it assumes that the particle surface is non-porous and uniform. The heat of adsorption for the first layer is higher than successive layers. The heat of adsorption for the second and successive layers equals the heat of liquefaction. Lateral interactions of the adsorbed molecules are ignored. So if we take this monolayer and we know the number of molecules, which is n sub m, and we know Avogadro's constant, and we know the surface area covered by one molecule of that gas, and divide that by the mass of the material, we can get the surface area per unit of mass. Looking back at the adsorption diagram, this area between A and B is going to be where our monolayer capacity will be found. Again, the monolayer capacity is when a single layer of molecules is adsorbed to the surface. And this corresponds to this region of the isotherm between A and B. And when we take that region and we use the BET calculation where C is the BET constant, it describes the affinity of the gas molecules to the surface of the material. So in other words, it's meeting the constraint of the heat of adsorption for the first layer of molecules is much greater than any successive layers. And when we take this equation and we put it in linear form, we can get some additional information from the line and use the slope and the intercept to calculate the monolayer capacity and the C value. The next technique for surface area determination is by air permeability. This technique involves taking a powder, placing it into a cylinder of known height and known diameter, and monitoring a pressure change as you pass air through it. So we're passing air through the powder bed and monitoring the pressure below and pressure above the powder bed and looking for that pressure drop. And from that pressure drop, we can calculate the surface area. It's a very mature technique. It's been around and written into many standards and used by various industries still to this day. The original instrument that made this type of measurement is the Fisher 95 sub-sieve sizer. It's a rather manual instrument. We also have more automated technologies that make the same type of measurement using air permeability. However, it's operated obviously from a computer rather than manual. So to calculate surface area from air permeability, we use the Cosini-Kármán equation, and we look at the cylinder diameter that's containing the sample, the sample density, which is why we need to measure it from the know it very well. The device can calculate the porosity of the powder bed, which is not the particles but the powder bed itself, so the space in between the particles. And we use the pressure drop, the length of the cylinder, aerodynamic viscosity of the gas, and then the flow rate, and calculate the specific surface area. We can do this measurement by maintaining a constant flow rate and measuring a pressure drop, or we can maintain a constant pressure drop and measure the flow rate. Just an additional note about this calculation. We're looking at the volume porosity of the powder bed, which is a dimensionless value, to calculate the surface area. And we get this value by looking at knowing the cylinder length, diameter of the cylinder, and the particle density. So again, the sample density is important. That's why we made those measurements. And we're looking for this epsilon, the volume porosity of the powder bed. And we get that by looking at the volume of the cylinder minus the volume of the material divided by the volume of the cylinder. So it's a ratio. And we can simplify that and calculate epsilon to go into the Cosini-Kármán equation to calculate the surface area. The third technique for surface area uses static light scattering, or more commonly known as laser diffraction. This technique again is primarily a particle sizing technique. However, it can be used to calculate surface area. We use Mie theory, and we're looking at light interacting with a particle and the light being scattered at different angles at different intensities, and those different intensities and angles are scattering functions, and from those scattering functions we can calculate a radius, so we can get actually a particle size distribution from the one analysis. And if, again, we know the density and we know the volume based on this measurement, we can calculate the surface area. To give you some additional insight into laser diffraction, and the calculations involved to get the particle diameter, we can consider the graphing the angle of scattered light versus the relative intensity of the scattered light. And we look at 125 to 149 micron sized particles. We can see a relatively high intensity and a scattering pattern that's relatively low in angle sizes. When we compare that to 33 to 44 micron size material, we can see that the intensity, maximum intensity drops, and we can see that the angle of the scattered light shifts to the right, which would make the angles larger. When we consider even smaller particles, we can see that the scattering intensity maxes out even lower, and we also see that the scattering pattern shifts again to the right, which means larger angles. So this demonstrates the principle of laser diffraction, that larger particles will scatter light at lower angles and more intensely than smaller particles. Smaller particles in this case would scatter light with less intensity but at much larger angles. When discussing these types of measurements, it's important to consider the theoretical constraints. In the case of laser diffraction, we're assuming that the particles are spherical and anisotropic, meaning that they have a nice smooth surface, no edges, no cracks, no pores, or any kind of surface features or irregularities. And if we don't meet that criteria, we have to redefine the size or the diameter as the diameter of a sphere of the same material that produces a scattering pattern that best fits the measured scattering pattern. In other words, when we're measuring the scattering pattern, we're collecting that data and we're trying to fit it into a model of theoretical spheres. And we're calculating a size result from the theoretical spherical model, not directly from the scattering pattern. The same is true when we calculate surface area from laser diffraction. It's an inversely proportional relationship on a log-log scale. In our case study that we were looking at, we obtained 3 commonly used metal powders, stainless steel 316L, tungsten carbide, and a tungsten, and performed surface area analyses by BET, air permeability, and laser diffraction on each of those materials. Here are the results for the stainless steel 316L sample. We used the gas picnometer using helium to calculate the density. The surface area results are in table 1. We can see laser diffraction, air permeability, and even BET are in somewhat agreement. BET was slightly higher. We'll discuss that later. The laser diffraction result, we made the calculation using the relationship that we determined at the beginning of the presentation, and we calculated that result from the size. Since we're dealing with laser diffraction air permeability, we thought it would be interesting to report size results from these different technologies. For BET and air permeability, which report surface area directly, we had to solve the relationship for particle size, so for diameter. So when we did this for BET to get our result, and we did this for air permeability to get the result. And then we also had to compare that to the weighted mean surface diameter, or D32, of laser diffraction. Note that typically laser diffraction reports results in terms of D43, which is the mean volume weighted diameter. In order to get the surface weighted diameter, we had to use the density to calculate that result in the software. But it's important to note that you have to compare surface area weighted results for size from laser diffraction to BET and air permeability. You can't really compare the volume weighted diameter, the D43, from laser diffraction. To get some further insight into these materials, we actually looked at them under an SEM. And here for the stainless steel, we can see a variety of particle sizes, mostly spherical sizes. And when we actually look a little closer and look at the size, this one's about 10 microns We see one here about 4 microns. This one is not really spherical, it's more elliptical. It could be about 8 microns or 4 microns depending on how it's determined. This one here, 15 microns. Again, mostly spherical, but then how do we classify something like this by any of the methods? So we're still assuming a spherical particle, but we have this irregular shaped agglomerate or aggregate. At the same time, if we try to zoom in on this image, we can see that there are some surface features and even some maybe smaller particles that could be fused to the larger particle. So there is some surface roughness that probably accounts for some of the difference between BET and air permeability and the laser diffraction. Since we're looking at an image, we thought it would be also interesting to calculate some surface area results using the inversely proportional relationship between surface area and particle size on a log-log scale, and see how that compares to the rest of the results that we collected. Here are the results for the tungsten carbide sample. Again, we used a helium pycnometer to calculate the density. We used the particle size result to calculate the surface area from laser diffraction. And when compared the 3 techniques, we can see they start to deviate from each other. In fact, BET surface area is 10 times larger than the laser diffraction result, and air permeability is somewhere in between. We also reported the particle size results, again using the weighted mean surface diameter, D32, to compare the different size results. We see the same type of relationship that we saw with the surface area. The volume diameter, D43, from laser diffraction was, of course, a little bit higher. There's no equivalent values from BET and air permeability. And again, remember we had to calculate the D32, the weighted surface diameter from laser diffraction, using the density in order to compare the results. The results for BET and air permeability size, again, we had to solve for the particle diameter using the relationship that we established earlier in the presentation. Looking at the image of the tungsten carbide material, we can see very small particles. This makes sense due to the values that we saw from the different techniques for size as well as for surface area. And when we zoom in to a small area here, we can see additionally that it looks like the particles may be fused together or aggregated, or they're definitely not spherical. They're very irregularly shaped. We can kind of make out some, so these two probably about 2.5 microns, and everything else looks to be smaller than that unless they're aggregated or fused together. We also used this image to calculate some surface area results for tungsten carbide. As you can see, there's a lot of little samples, little small particle sizes in there. So when we use this inversely proportional relationship between surface area and particle size on a log-log scale, we can see the, again, as the particle sizes get smaller, the surface area increases based on this calculation. Moving on to tungsten, again, calculated the density using a helium pycnometer. We have the surface area results here. BET showed the highest result. Laser diffraction showed the smallest result. We used the D32 value to calculate the surface area from laser diffraction. Again, calculated the particle size from these different techniques. Again, comparing the weighted mean surface diameter, D32, for laser diffraction, and comparing that to BET and air permeability result. The weighted mean volume result could not be used again because there's no equivalent value from BET and air permeability. And then the calculation for the BET and air permeability result again uses the same formula that we used earlier. Looking at the image of the tungsten, it looks similar to the tungsten carbide, where we see some aggregation or agglomeration. The particles seem to be in the same vicinity and maybe stuck to each other. When we zoom in, we can see some additional details. Some of them again look like they're maybe fused together. Some of them maybe just huddled around each other. And we could kind of make out a couple of particle sizes here, 1 micron for these two. This one looks to be about maybe 2 microns. For this image, we also made some surface area calculations using the density of the material and the inversely proportional relationship between surface area and particle size. And again, using that calculation, we established, that the same trend where as you decrease in particle size, you increase in surface area. Summarizing all the surface area data for the 3 techniques and the 3 materials in one place, we can see that the laser diffraction, air permeability kind of agreed with each other when it came to spherical particles that were relatively large in size. BET also agreed to some extent. However, BET seems to be more sensitive to surface area because of the gas adsorption technique that it's used. We can see higher surface area results from BET, and we see lower surface area results from laser diffraction and air permeability. Air permeability was not as low as the laser diffraction results, but they were still a little bit lower than BET analysis. Summarizing the particle size results, we can see a similar relationship. In this case, the laser diffraction and air permeability agreed for the stainless steel, which was mostly large and spherical. BET slightly undersized it because of its sensitivity to surface area. Tungsten carbide and tungsten were mostly small and aggregated. So we saw a very large surface area, which gave us very small particle sizes by BET and air permeability. The largest particle sizes were determined by laser diffraction. So now for some concluding statements on the study that we performed. It's important to note samples were not pre-treated to remove aggregation affecting size, nor to remove surface reactions affecting density. We did notice that the sample densities that we calculated were a little bit lower than the theoretical. I think that could be some surface materials or oxidation or something on them. The samples were degassed of adsorbed moisture prior to gas adsorption analysis, though, so make sure to keep those in mind. The 3 stainless steel surface area determinations were similar. The particles were mostly spherical in shape. We saw that in the image, but they had some surface features such as cracks and pores. So the BET surface area was slightly greater than that from the 2 particle sizing methods. Tungsten carbide surface area results differed greatly. The sample is definitely not spherical and highly aggregated. This will explain the difference between the surface area determinations and between the particle size results as well. And the tungsten surface area results differed among the determination methods, but not to as great as an extent as the tungsten carbide. Tungsten particles did show more spherical shape and were slightly less aggregated than the tungsten carbide particles. The surface area results for the tungsten carbide was the highest of the 3 materials by all 3 techniques, while those of the stainless steel was the lowest. This is consistent with the particle size distribution results, where the stainless steel were the largest, while the tungsten carbide were the smallest, due to the inverse relationship between size and surface area. Additionally, BET analysis gives the largest value for surface area, especially when particles are not spherical and have some surface features. Laser diffraction gives the largest value for particle size and the smallest value for surface area. The surface area and particle size results from air permeability show the most agreement with laser diffraction when the particles are spherical. And now I'd like to thank you for your attention. I guess we'll take any questions, but first I would like to thank my colleague Tony Thornton. You can contact either one of us if you have any additional questions or
Thank you, Jack. I'm opening the chat for everyone's questions now, and we already have a few. The first question is, if BET is best for surface area and light scattering seems to be recommended for particle size, when would you use air permeability?
Well, it's interesting. Actually, air permeability, it's not really a technique that I guess focuses on the particles themselves. It's more of a bulk property of powder. Being that the case, we're looking at how air passes through a particle bed. So any kind of applications where passing some kind of air or something for like to fluidize a powder bed or anything like that, or at least try to get some gas molecules in between a powder bed, things like explosives or fireworks or any kind of metal powders where you're using for ammunition, those types of applications typically use air permeability as part of their characterization in addition to surface area by BET or particle size by laser diffraction. So in those types of cases, it's very useful. And again, as I mentioned, it's a bulk powder property, so it could affect other things with regards to a process. At the same time, it's a nice and quick measurement to make. Gives you a quick value for a relative fineness of a material, or if you're looking at a grinding process or something like that. Typical analysis takes from start to finish, from preparing the sample, introducing it to the instrument, making the measurement, and then cleaning up, as probably less than 5 minutes. So for a continuous manufacturing facility, it's pretty reasonable just to kind of get an idea of how fine or how coarse the particles are.
I have a follow-up question with respect to permeability. Just relating back to one of your slides, can you elaborate a little bit more on how to obtain the volume porosity of the bed?
Yes, sir. The volume porosity of the bed, I guess, again, I mentioned it was dimensionless. It's a ratio of the powder, the volume of the powder and the container, and we're dividing that by the volume of the container. So we're looking at just the volume fraction of the empty airspace in between the particles. So obviously, the larger the particles, the more interstitial spaces there are. The smaller the powder is, or the particles are, the more they'll be more compact, and less air will be passing through. There's less space in between the particles. So when we characterize it like that, it gives us, like I said, like a bulk property of the powder itself, as well as surface area and particle size.
I have another question here about preparation. Can you elaborate a little bit more about what type of preparation is required for each of these methods?
Sure. So for BET analysis, typically we're looking at we have to make sure the surface is clean, first of all, because we're looking at the particle surface interacting with the gas molecules. So we don't want any kind of side interactions or reactions or anything like that. So we have to usually degas the material, sometimes heat it up, and we want to remove any kind of adsorbed materials like water or CO2 or things like that. And the amount of time it takes or the amount of preparation it takes varies from material to material. In the case of the metal powders that we used, they were, they don't really attract a lot of water or a lot of moisture or a lot of things from the air. Not a lot of side reactions occur, so they're relatively easy to prepare. Other materials sometimes take a little bit more. With light scattering, obviously we're dispersing the material and some kind of fluid, which is either air or liquid. And with a liquid dispersion, you have to worry about surfactants and agglomeration and deagglomeration. So there's some preparation there with how much ultrasonic probing you have to do, or sometimes circulation, or how much surfactants, or maybe adjusting pH of the water, things like that, or even which solvent you're using. You're using water, you're using alcohol. With these materials, obviously, like metal powders, we just use water. It was perfectly fine. Air permeability doesn't really take that much preparation because we're just putting the powder into a cylinder and placing it, and a piston comes down and compresses the sample, and you're passing the air through it. And all we're doing is looking at the pressure below and above the powder bed. So there's not much preparation work involved, which is also nice because you get to analyze the sample in a more of a natural state because there's no preparation involved. It actually can give you a little bit more information about your process because we're not worrying about breaking up agglomerates. We're not worried about cleaning the surface or anything like that. We're looking at the raw material itself. So like I said, prep work from starting the preparation to analyzing to cleanup, probably about less than 5 minutes.
So I have a question from a user. I have samples that have a 30 micron particle size and the surface area is very high, 160 meters squared per gram. Why do these large particles have such a high surface area?
Well, like I said, when we're talking about particle size, we're talking about, especially I guess when we're measuring it, assuming by laser diffraction, we're assuming that the particles have a nice smooth surface. With this type of material with a high surface area, that typically means that the material is very porous. So all those pores contribute to additional surface area that's available for the gas to interact with. So that's probably the most likely case, is that you have a very porous material.
Okay. When you compare the surface area via BET and air permeability, in some cases you saw the same surface area, in other cases you saw some disagreement between the two. Why is there some difference between those two methods?
So one of the constraints of air permeability is that it doesn't really take into account the pores in the particle. So if a particle has a lot of surface roughness or a lot of porosity, it's a little bit difficult for air permeability to take that into account. Again, because of its nature of being a bulk property of the powder, as opposed to the individual particle property. But with BET, the gas can interact with the pores. It can interact with any exposed surface, whether it's inside the pores or on the surface of the particle itself. And that's why you see like a greater surface area related with BET and less so with air permeability. And again, when I was mentioning laser diffraction, I'll just throw this out there also, that it's assuming that the particles are not porous and have a nice, smooth, uniform spherical surface.
For your BET results, and particularly on the stainless steels, was the BET result, is that from nitrogen adsorption?
I think we use krypton for those measurements. These are, I think, I think it has like a lower surface area, so I think we use krypton for those measurements.
For the air permeability measurements, do you make any compensation for particle shape in those calculations?
And just like all the other techniques, it's still assuming a spherical model, but so it assumes that the particles are spherical. But again, it's just the nature of the measurement being a bulk property of the powder, and quick analysis. It doesn't really take into account any shape factors. Shape will affect the way it packs. So if the shape is a factor in terms of how it packs or how it compresses, then you'll see different variors. So if you have oval shaped particles that pack a certain way and spherical particles of the same relative size, they'll pack a different way. You might see if the oval shaped particles are packing much better, you'll see a higher pressure drop because you have more resistance to the air flowing through them, through the powder bed, which would result in maybe a lower surface area.
The particle size you obtained from BET, does that relate to the D50 by light scattering, or can you elaborate a little bit more on that relationship between calculating particle size from BET and how to compare it to what's obtained from a more traditional particle sizing technique like light scattering?
So the measurement, I guess the value that we use, the D32, which is the surface area weighted mean diameter that we compared to the BET and air permeability, that's the summation of all the entire distribution of particles averaged into one value. We report the same thing for volume, and that's typically what's reported by laser diffraction. However, we had to use the density to convert it to surface area because we needed to know the mass per particle. So it's an average value of the entire distribution. It's not necessarily the D50 of the distribution.
And then there's a follow-up to that question. Which specific surface area method would be more precise based on the average particle size?
So based on the average particle, depending on what the application is and what you're looking for. If you're looking for some kind of absorptive material, or you're looking for some kind of maybe type of using the material, the powder, for some kind of reaction, surface area by BET is probably more precise because you can get really detailed information about the surface area. If you're looking for a quick measure, just to get an idea of the relative surface area or relative fineness of a material, air permeability works well. If you don't have any of those techniques, you can still get some information from laser diffraction if you have a laser diffraction instrument for particle size. The only thing is you need to know the density of the material, and that can be also kind of tricky if you have a mixture of different particles, but that's a whole other story.
Which of these techniques gives the most accurate or reliable measurements of the surface area?
Again, similar to what I just stated, it really depends on the application and how much detail you really need for surface area. If the particles are spherical, they all seem to be, in agreement with each other. If there's some surface features or surface roughness, BET will give you a little bit higher surface area. It's all really, like I said, relative to the application. How are you using the material? And typically what you want to do is you want to make some kind of characterizations on your material based on how you're using it. If you're using it, again, for maybe some kind of like in catalysis or some kind of other type of place where you're looking for a reaction, then BET is probably a better choice because it gives you more detail. If you're looking at just monitoring a grinding process and you want to do some quick measurements throughout the process and get some ideas as to how fine or how coarse the material is, if you should continue to grind it some more, increase the time, decrease the time, increase speed, decrease speed, things like that. Air permeability works really well. And again, laser diffraction, if you're already getting a particle size distribution all you need is the density, and you can calculate surface area, and it'll still give you a result. You just have to keep in mind the constraints of how laser diffraction calculates the results, and it may not, based on the data that we saw, it may not always agree when you have irregularly shaped particles or porous materials.
Our next question is on pyknometry. Why did you use helium for your pyknometry analyses?
You can use, typically people use either helium or nitrogen. It really doesn't make too much of a difference. One of the main differences is that helium is relatively small, but at the same time, it doesn't really interact with the metal surface that much. Sometimes when you're working with organic materials like pharmaceutical materials and different things like that, you will probably want to use nitrogen, just because the helium is so small that you may actually penetrate the surface of the molecule, the carbon-carbon bonds in the molecule or in the surface. So sometimes it may not work very well using helium for organic materials. So you'd probably better off switching to nitrogen, which is a larger molecule. But like I said, in the case of looking at metal powders, either one would have been sufficient. We just had helium available and ready to go, and we just used it.
So this next question relates back to particle size and surface area. Do the results that you presented and your conclusions, does it really indicate specific surface area for a material is also particle size dependent, and are there any other dependencies as well?
The surface area, yeah. Well, we saw that again, the particle size, there's like the inversely proportional relationship between particle size and surface area. So there is some dependence on the particle size. So as you get smaller in size, regardless if we're making the measurement by laser diffraction or looking at the SEM image, as you get smaller, the surface area increases, because it's the total composite specific surface area of the material per mass of material. So it's the surface area per mass. So given that same mass, you get varying results from the different techniques depending on the surface features and things like that. But the dependency on size is related to the smaller particles having more surface area in the composite value versus larger particles having a lower surface area in the composite value.
We have another question on density, Jack. Can you elaborate and discuss a bit more on how you measure and determine that particle density?
Sure. So the way the gas pyknometer works is that you have an empty chamber. In the simple form, you have an empty chamber where the sample is going to go. You get the volume of that chamber by flowing gas into it, and you're monitoring pressure. So we're using the ideal gas law, PV equals nRT, and we're looking at pressure and volume and comparing pressure and volume. So you have the volume, you determine the volume of the empty chamber without the material, then you determine the volume of the chamber with the material present, and you take the difference, and you're looking at the amount of volume of the material that it displaces, how much gas it displaces inside the container. And from the volume, and we weigh the sample before we enter it into the instrument. So we'll have the mass and we'll have the volume, and we can calculate the density.
We have another question on BET surface area, and in your case study, it primarily focused on materials that didn't have significant porosity. Is BET useful for highly porous materials?
For highly porous materials, yes. It's definitely useful. That's probably the main application for BET, is looking at very porous materials, because it takes into account all the surfaces that's available for, like I said, whatever type of application you're using the material for. if you need to say, for example, you put the particles that you're measuring into some kind of slurry for some kind of process, you may have some trapped gas in those pores. So knowing how much available pores, how much surfactants you need to add, how much additives you need to add to make sure that you don't have any gas trapped inside the particles, which could affect how they their bulk density inside the liquid. You want to make sure that it's all dispersed very well. So the porosity, the BET is definitely the choice for surface area if you're dealing with highly porous materials. That tells you a lot. If you're looking again, using laser diffraction, it's assuming that it's a solid, smooth sphere. So it doesn't take into account the porosity, which is why we saw that big variation between size and surface area between laser diffraction and BET.
With respect to the permeability method, what are the limitations of the air permeability method?
Well, I mean, the limitations obviously is the size of the material. There's some size limitations. It doesn't. I think the upper size limit for the instrument we have is I think 75 microns, but it's mostly involved with can you get 1 cubic centimeter of the material into the sample cell, the sample cylinder. That's the mouse. So we need to know the density in order to weigh out the sample to figure out how much we need to fill 1 cubic centimeter of volume inside the tube. So really that's the primary limitation, is how much sample you need to use. One of the more common and industries and applications for this technique is actually metal powders. They like to use it for various reasons, and it's a traditional technique. It's mature, it's been around for a long time. They have historical data on it, on the materials using this technique. But other than that, there's not many limitations to it.
The next question is with respect to particle sizing. Laser diffraction particle size distribution values are sensitive to dispersion. How did you investigate this?
Well, again, we didn't. When we were using the metal powders, they didn't have too much. If there's any kind of side reactions or any kind of like surface reactions like oxidation or anything like that, it won't really affect the dispersion. And we dispersed it in water. I can't remember the surfactants, if we use any surfactants. Typically, we use sodium hexametaphosphate as by default, it's just a small concentration of that. But it's it's standard analysis. We've measured these materials before many times. But there's some, typically we'll just make measurements if we're investigating an unknown material by adding, trying different surfactants and different concentrations to see when we get a repeatable result for a size distribution.
The next question refers to surface area. How do you think aggregation affects surface area, and can the gas molecules penetrate and reach the surface of particles if they're in an aggregate?
If they're in an aggregate, you're still going to have some open spaces in between the particles. So it's going to look at it as one big particle with surface roughness. And if there's any open spaces, it's going to treat those like pores. So it may not totally, occupy the entire space of exposed surface if that surface is fused or attached to another particle in some way. But any kind of gaps or any kind of like openings is going to be looked at as a pore. And if it looks at it that way, you'll have some increased surface area, but maybe not as high as you would if you had the particles deaggregated or deagglomerated.
So the next question is a little bit different than particles. One person asks, can I apply any of these 3 methods to thin films?
Um, the BET can probably be applied to a thin film. Laser diffraction will be difficult. Air permeability, probably not. It'd have to be folded and cut into a cylinder that would fit into the cylinder, the cell holder. But BET analysis can probably give you some results because you just place the thin film into the as long as you know the dimensions and you know the size of the aliquot you're using and the mass, you can probably use BET for that.
So this is another surface area question. When performing surface area measurements, is it the best practice to do measurements with more than one technique, or is one technique sufficient?
Usually you want to do, depending on the application, but typically sometimes it's good to use more than one technique because one technique may not give you the entire story. It's very common for someone to have a laser diffraction instrument and a BET instrument in their lab analyzing the same material because again, you know, you can get size from laser diffraction and you get surface area in terms of like a porous material from BET. Some applications where you're looking with working with maybe some explosives or munitions or fireworks or things like that, where you know, laser diffraction would give you the size distribution, whereas air permeability would only give you a single value. So you can get a size distribution and a average size and a porosity of a powder bed from air permeability. So those types of applications would probably need two techniques to characterize the material. In some cases, you could use all three. It just really depends on the needs and the application. But it's always, you know, better to try to get the whole story about a material, because in some cases you may have the exact same size distribution by laser diffraction, and you may be using it to calculate surface area, but one lot of material may behave a different way than others, and you'd have to use some other technique, like maybe it could be the particles became more porous, or maybe they're not flowing very well, they're not the permeability is not well good enough for whatever the process is. So additional information can always help.
So this is another surface area question. For fragile samples, in this example, lyophilized cakes, would BET damage the sample?
BET shouldn't damage the sample. We're not really going to really high pressures or anything like that with BET. So we actually have an application where we actually look at lyophilized materials in a tube, and it shouldn't cause any kind of damage or anything like that. For especially, it just depends also on the preparation. If the preparation is simple, then it should be no problem.
Okay, and another question related to surface area. When we compare the BET result of the same material, do we need to specify the test condition in order to make the results comparable? So I imagine this is with respect to if we're exchanging data with another laboratory. How much information do we have to give them so that we both understand we're making the same measurement?
Yes, you'd have to definitely share the details of the measurement, what type of gas you're using, what kind of prep station or prep times you're using, if you're heating it or cooling it, or you know, if there's a cooling process after the heating process, anything like that, the amount of sample of course you're using, and sometimes, you know, the software or the instrument that you're using may have some variability. So you have to make sure that you try to communicate as much information as possible to make sure that the results are comparable, because one set of results may be correct for one set of conditions and another set of results may be correct for a different set of conditions, but the two results may not agree with each other. So the conditions and on how it was analyzed are very important to communicate.
We're just about out of time, so one final question for this morning.
Sure.
How reproducible is air permeability, and how does are there packing effects that could impact the results?
There's not really many packing effects, because once you have 1 cc of the material in the tube, the instrument compresses it. The piston comes down and compresses it and blasts air through it and monitors the pressure change. And you're also recording the weight. So you're weighing the sample, and as long as you're careful transferring it over into the tube, as long as you are doing it the same way and you're careful not to lose any material, it's very repeatable. The reference material that we typically use with this instrument is a 1 micron tungsten powder, and it behaves really, really well. It's a non-destructive technique, so you could actually use the same aliquot of material that's pre-weighed, and just making sure that you're weighing it accurately each time, and you're not off by a few milligrams here or there. And as long as you're transferring it to the container and making the measurement, it should be, fine. But if the particles are big and they're irregularly shaped, you might have some effects. But in that type of situation, all the techniques will be affected the same way. Shape will, affect the particle size by laser diffraction. Shape will affect how it packs in the air permeability device, and then shape can also impact BET analysis if the material is like either has a smooth surface or a porous surface or any kind of surface roughness to it. Those types of impacts can occur as well.
Thank you, Jack, and I'd like to thank everyone for attending this webinar. There was a great response for the number of questions that were raised, and we will get back to everyone and answer any questions that unfortunately we could not get to today during the webinar. Jack, is there anything you'd like to add this morning?
I'd just like to thank everyone for attending, and I hope you found this webinar informative and useful, and help your understanding. And if there's any questions, feel free to contact us. I'd also like to mention our online training portal that you can get to through our micro.edu website or the micromeritics.com website. We have online training available that covers the use of BET instrument, our picnometers, and our air permeability device, and it's all free. Just log in, register, and you can take the training and earn a certificate. So if you have any questions about that, just please let us know, and we look forward to supporting you in any way we can.
Great. Thank you, everyone, for participating in today's webinar. We hope you found it useful and beneficial. Please don't forget to check back for upcoming webinars on micromeritics.com/webinars, and we hope to welcome you again very soon. Thank you and have a great day.
Thank you.